Hello, I'm Jared Skeens, and welcome to the Zoom room. Today, I'd like to talk about Pure Maths 1, Functions, Part 5, Transformations. Now, this is going to be a little bit interesting because the transformations part of the functions unit is part of the new syllabus. So, as of right now, there have not been any questions come out on past papers, but it is in the syllabus. So what I'm going to do is I'm going to focus first of all on training your mind. Of course, if you have watched my videos or if you've been one of my students, you know that I like to train your mind before I train the skill. Sometimes it makes my videos a little bit longer. So what I would suggest is you take good notes. That way, hopefully it doesn't get quite so boring. But it's important to train your thinking. I find a lot of students really struggle with graph types. And even though it was taught, at least from the curriculum that I used back in IGCSE material, students very quickly forget it. And so we're going to review just a little bit, and I'll focus on training your mind. I will use some examples for the skill of graphing to illustrate these transformations. But I do not yet know how Cambridge is going to implement this topic into its exams. I'm sure they will find interesting ways of correlating transformations, especially with quadratics. Obviously, it's in the functions unit. So we'll have to see moving forward how they do that. So I can't really use any past paper examples because right now there aren't any. But I'll do the best that I can to mentally prepare you and also give you that extra graphing skill, and hopefully it will enrich your overall understanding of graphs, because we already saw that you have to do some sketching involving quadratics and functions. So this will only enrich and give you a broader skill set. And then whatever application that Cambridge does give to you, hopefully you'll be able to adapt to the question type. So let's get started. We actually have a lot of work to do. What I'm going to do first is I'm going to do a little bit of review. Now, the curriculum that I used for IGCSE, it wasn't from Cambridge. It was a different curriculum, but it did cover what I call parent functions. A parent function is the most basic version of a particular function or graph type. So what I've put up here are just 6. There could be more. I'm just going to quickly go over 6 that I know that I covered back in IGCSE material. I'm sure that by the time you get to the A-level material, you've probably forgotten it already. So one of those parent functions was the x squared, the quadratic function. And remember I said, if you watch my video on sketching, that your sketches don't have to be very accurate graphs. They're general visual representations. It's the main graph characteristics and just general correctness that you need. So what I call 3 points of reference. So on a parabola, you know that parabolas have an axis of symmetry. I don't know if you can see my little dotted line right down the middle or not, but there is a dotted line there. So the key point on a quadratic is the vertex. It's right on the axis of symmetry. So that's point 1. And then, of course, you can plot a second point, and you can use the axis of symmetry to reflect it to get the third point, and you get your 3 points of reference. So we already talked about quadratic graphing when I did the video on sketching. or actually I did it back in quadratic section also. So in quadratics, there's a sketching, and also in functions, there's a sketching. So then we move on to, this is the square root function. And actually, I'm a little surprised that curriculum don't take advantage of this function more than what I've seen. It's very helpful in demonstrating reflections. It does show up algebraically, but I haven't really seen some curriculum, I don't think, take advantage of the graphic nature. But this one has a domain statement. If you watched my video on domain and range, you know that we cannot have negative numbers in the radical. That takes us into complex numbers. And so x must be greater than or equal to 0. So what we end up with is an end point, and it curves off in this direction. So this would be 1 point of reference, and then you plot 2 more points and you get your 3 points of reference. Then we get over here to what's called a reciprocal function. And actually in IGCSE and in the A-levels, you do see it algebraically show up quite a bit. Again, they don't generally require you to graph it, although they do sometimes take, they'll use the domain to limit it to one side of the graph or the other, usually the positive side. And again, there was one of our sketches from the functions video where we did use part of a reciprocal function. So this one I find is often not understood very well by students. And I think the reason is because a lot of curriculum doesn't really take, they don't really take time to develop it well so that students can understand it. A couple of the things that you need to know about a reciprocal function is obviously the domain statement. In a fraction, you cannot divide by 0. So the fact that you're not allowed 0 in your answer set means your graph cannot cross the y-axis. Okay? You're not allowed to have that value. So it creates what's called a vertical asymptote. I know it's a big word. Don't really have to worry about it. But this vertical asymptote means your graph cannot cross it. Think of it as like a fence line. You have a fence, and you can go up to the fence, but unless you have a gate or something, you can't really go through the fence. And so think of it as like a fence. And reciprocal functions fall under a broader category called rational functions. Now, rational functions can get quite complicated and can be, it would take at least another video, if not 2, just to explain how to graph rational functions. Obviously, we're not going to do that. But in rational functions, what you do is you compare the exponent of the variable on the numerator with the exponent in the variable of the denominator. And in this case, obviously, there's no variable in the top, meaning the exponent on the variable in the numerator is less than the exponent on the variable in the denominator. I know that's kind of a mouthful, but because the top exponent is less than the bottom exponent, that means you're going to get a horizontal asymptote at 0. Like I said, reciprocal functions are part of a larger category, but some students don't understand where this horizontal asymptote comes from. Another way of looking at it is has to also do with end behavior of your graphs as they go off towards infinity and negative infinity. The point is we get these 2 sections of our graph. That's what's going to be important. When we talk about parent functions, you should be able to visualize the basic graph that represents that, okay? So that's what's going to be important here. And our 3 points of reference are the 2 asymptotes and an additional point. So one asymptote, two asymptotes, the point, that's your 3 points of reference. On this side, we have two asymptotes and also a point there. So that's going to be important. And the key is actually where the asymptotes intersect. So I call it like the center. That's going to be important. When you get into the transformations, especially translation, moving something around, it's your key point that's going to help you move the graph, okay? Then there's cubics. Cubics have what's called a flex point. Flex point is where concave down meets concave up. So if you have a concave down and it meets concave up, you can see there that you get this curve one way and then it curves the other way, and where they meet creates a flex point. So you get this curve, so that's an F for flex point. And again, that's our key. And then you have two other points of reference. If you reflect it twice, once over the y-axis and over the x-axis, you can then get the third point. So those are cubics. This is your, some people call it absolute value function. It's also can be called modulus. So modulus and absolute value are just two names for basically the same thing. And so here you get a vertex again. When x is positive, the absolute value of a positive number is still positive. So as x goes in the positive direction, your y is positive. As x goes in the negative direction, your absolute value of a negative changes it to positive. So it goes up again. So this is an absolute function, absolute value function or modulus function. Then you have the exponential function. The exponential function is kind of introduced in the IGCSE material. Again, they don't really spend a lot of time, or at least the curriculum I used didn't spend a lot of time really explaining it well. When you get to transformations, it's a little bit tricky. This horizontal asymptote has to do with your exponential base has restrictions. It can't be zero, and it has to be positive. Can't be zero or negative, and it also can't be one. So since it can't be zero or negative, then that means a positive base raised to any power also cannot be zero or negative. So you get this horizontal asymptote. Again, this will be explained more to you in future A-level material. So these are just 6 parent functions. The most basic version of the function type or graph type, that as soon as you see quadratic or root or this graph should be what comes to your mind, the general picture. Transformations, of course, are going to manipulate it in some way or another. That's what we want to study in this video. Now, to make things easy on us, I'm not going to cover cubics because cubics will show up in Pure Math 3 and polynomial, the polynomial section. Modulus also shows up in Pure Math 3. And exponentials and logarithms also show up in Pure Math 3. So all 3 of these are not quite as essential for you right now. What I want to focus on are the things that will help you in Pure Maths 1. You're dealing with functions, and like I said in the first functions video, the primary focus of Cambridge in the functions unit is on algebraic. So we'll focus on this here, or trigonometric, and you can watch the trigonometric videos to help you with the trigonometric graph types. So I'm going to focus on these 3. These 3 will be the most helpful. I'm going to use the reciprocal function to illustrate translations. I will use the square root function to illustrate reflection, and I'll use the quadratic function to illustrate what's called stretch. I put /shrink. Stretching can be stretching to make bigger, but stretching actually also covers what I would call shrinking. Just like if you're familiar with transformations of objects, you have enlargement, and sometimes the object gets bigger, sometimes the object gets smaller, but I don't think they call it enshrinkment, just enlargement. So they just call it stretch, but I put /shrink. Then there's going to be a combined, where you mix more than one transformation together. So in this video, I'm going to focus on each one of these separately. We have to cover both the X variable and the Y variable. And then I will give a separate video so that this isn't too long, to cover combined transformations. There's a couple of other issues that we need to deal with when we start combining transformations. So I want to first of all go over these 3 types that you will need for the Cambridge Pure Maths 1 transformations of whatever function they give to you, okay? So translation is going to be moving a graph left or right, up or down. Reflection is going to be flipping a graph over a particular axis of symmetry. And then stretching it is going to be, of course, stretching it along a particular axis, or shrinking as well. Okay, so let me set up for our first type. Okay, here we're going to talk about the first of our 3 types of transformations. So for each type, we need to look at 2 different things. We need to look at the horizontal transformation. That's going to be the left and right. It's going to involve the x-axis. We also need to look at the vertical transformation, which has to do with the y-axis. Now, to do this, I'm going to do 2 things. The first thing I'm going to do is I'm going to try to help you mentally understand it from a purely algebraic illustration to help you see or know what you're looking for, okay? Then I'll go back and use one of our parent functions to illustrate it graphically. So you'll get to see it 2 different ways. One is an algebraic representation, so you know what you're looking for. The second will be a little bit more the graphing skill set of what to expect to see, or if you have to draw it yourself. So I'm not sure if Cambridge is going to have you explain a graph that they draw, or whether they're going to give you the transformations and you have to draw it yourself. Either way, you should be able to go from the algebraic explanation to the graph, or from the graph to the explanation. So this really involves more mental understanding than it does skill set. So I hope you're taking notes. That way the video won't be so boring. I'm sorry that the videos are a little bit long, but it's really important to me that you don't just do math. That's what makes students frustrated, is they do math, but they don't understand it. So I'm trying to help you understand it so that it makes sense what you're doing, and it will make you, hopefully, or help you enjoy math a little bit more. So here we're on translation. Now this is my rule of thumb, or my guide to help you. Take the new function and compare it to the old function, okay? Take the new and compare it to the old. How is the new one compared to what the old one looked like? Okay, that's going to be kind of our guiding principle to help us visualize what's going on here. So if we look at it with respect to a coordinate, we're going to have the x coordinate and we're going to have the y coordinate. So what we have, so if we look at it as a coordinate, we have the original function. The old one is what I'm calling the original. So you have your x, and remember f of x is your y. So it's like your x coordinate, your y coordinate. Your x coordinate is the independent one, the one you select values for. The y1 is the dependent one. It depends on what all the calculations come up to. So this is our x, this is our y. Notice I put subscript 1 to represent the original or the old one. Now, a transformation is going to be added to it or multiplied, or you're going to see something done to the original function. So when you look at the new function, now we have x subscript 2, and we have a function in terms of x subscript 2. So this is our new x and our new y. This will help guide us mentally through this process. So translation is our first type. I hope you're ready. Hope you got ready to take notes, and we're going to move along through this. So again, there's the horizontal, which affects the x. The vertical affects the y. Here is our original function. Y is some function that is written in terms of x. We know that you can replace f of x with y. So this is just going to represent any particular parent function. Y equals f of x. The function of x is any one of those parent functions. I showed you 6. There's more, but I just showed you 6. So probably the most important ones will be the quadratic one, obviously, and who knows what else they use, okay? But they all apply the same way. Once you understand how one works, it applies to all of them, mostly the same. The exponential one's a little different, but we're not covering that one, okay? So if this is our original function and we're going to do a translation. Translation, remember, means we're just going to take the graph as you see it and you're going to slide it either left and right or up and down, or a combination of left and up or left and down, like that, okay? So to make a translation, you're either going to have a value added to the x, or it's going to be added to the y, the function of x. Remember, y is your function of x. This one is horizontal. It's connected to the x. Now, how do we think this through? Well, what you do is this new one, this is your new function, x2 plus a, replaced your original x. This in here replaced that. So if we compare the new to the old, that means our x2 is equal to x1 minus a. So it's the old one, subtract a. If we look at the y value of this, it was only the inside of the function that changed. The outside of the function, meaning the f, the function itself, did not change. So our y2 is still equal to our y1, meaning no change. So if we can write translations as a column vector. If you remember studying vectors, a column vector tells you how to move from one point of the vector to another point using your x and y coordinates. So a column vector uses this. That's a column vector. Your x movement and your y movement to get from the end of the vector to the head of the vector, okay? So your column vector for this would be negative a for the x. Your x is moved a negative a units. Your y is not changed at all. So Cambridge might give you a column vector representation, or they could give you an algebraic function representation, or they could give you the graphic representation. So the graphic one is what I'll cover to illustrate it after I go through the algebraic. Okay, so here's the algebraic. Here's column vectors, another way of showing it. If we look at the vertical, that means instead of moving it left and right, if we want to take our parent function and move it up and down, then what you want to do is notice that your x's did not change, meaning x2 simply replaced x1. There's no change to the x. Your y2 is y1 plus a. So in other words, you took the function from here and all you did is added a to it. This gives us a column vector of no change for the x and a plus a for the y. Okay, so these are two different ways that you can represent it. You can represent it in an algebraic function. You can represent it with a column vector with these movements. Negative a in the x, remember this has to do with the x direction, no change in the y direction, or no change in the x direction, and a plus a in the y direction. Okay, so I hope you took this down as notes, and let me change it over and we'll look at the graphical representation of this. Okay, here we're back, and now we're going to look at the graphical representation. So you really need to kind of correlate all three of these. What's going on with the algebra? What is the possible indicator that Cambridge could use to represent it, like the column vector? And also, what is the graph supposed to look like? Now, to represent our translations, I chose to use the parent function of the 1 over x, or the reciprocal function. Notice here, the plus 2 is connected to the x, whereas over here, the plus 2 is actually connected to the function. So this is a horizontal translation. This is a vertical translation. Now, if you want to just review the algebraic real quick, notice that this would be our new function. Our x2 replaced the x1, where actually if you wanted to write this as the graphic one, it would be y1 equals 1 over x1. So this is now our 2's, the new function. So our x2 plus 2, subscript 2, subscripts have no mathematical value. So our new x value plus 2 replaced the old x, meaning if you take the new compared to the old, I had it in black, not that it really matters to you, I like color coding, it's the old one minus 2. The y's did not change. There's no number added out here to the function itself. So nothing relates to the y value, okay? So actually y2 is still equal to y1, no change in the y. This one over here, your x2 just replaced x1, no change in the x. But your y2 is now the y1 function plus 2. It's outside the function, okay? So the change is on the y-axis. So again, just to go over the algebraic part with numbers, so the column vertex, or sorry, the column vector would be -2 for the x, no change on the y. Over here, it would be no change on the x and 2 on the y. Okay, now we said we want to focus on the graph. So I'm going to get rid of the algebra. And let's look at what the graph does. Now remember, quickly, your parent function for this graph type had asymptotes right here and right here with a basic graph that had a dot like this and went curve like that, and one here, and went like that. Notice it's a sketch, doesn't have to be perfect. So what's important to us is this center of where the asymptotes intersect. So if we take our graph here, and in this one, notice that whenever something is connected to the x, it changes the sign. So if this is a +2, it's going to end up going negative. If this were a -2, it would end up going positive. Whereas when it's connected with, when it's connected mentally with the y value, it does not change the sign for these particular translation transformations. Okay, so what we want to do is we want to take that center and we want to move it left 2 units, but up and down none. There's no change. So this then is where the asymptotes cross. Okay, so probably got this in my way here a little bit. We already got it there. That was -2, 0. So we moved that center. Now we're still going to have, and you could plot a point, you could plug in a point to figure it out. For example, if x is -1, because now we're over here. So if you're at -1 plus 2 is 1, 1 divided by 1 is 1. Notice it's up here, and this goes like this, and up like this, means this is going to go here and go like this. Remember, again, it's a sketch. So you can plot as many points as necessary if you need the accuracy. Again, I just go with 3 points of reference, the 2 asymptotes, and I plotted 1 point. So a -1, 1, here would be 1, 2, 3. This would be a -3, -1 over here at this one. Okay, so this was -1, 1. So if we go from our center over 1, up 1, then we're going to go back 1, down 1. There's a symmetry here. Okay, so that's what this graph would look like. If we come over here, this one gets moved up 2. So if we go up 2, that's our center point. Here's our asymptotes. If we plug in the value 1, 1 over 1 is 1, plus 2 is 3. 1, 2, 3. Notice we still get basically in that same corner of the asymptotes. Goes this way, goes this way. So if it's over 1, up 1, it's back 1, down 1. It would be at -1, 1, and goes like this and goes like that. Okay, so they're really not that difficult to draw. You've got already your 2 points of reference, and then you can just plot a point and use reflection to get the other one. So this is only horizontal. This one is only vertical. Guess what do you think is going to happen if we come up with a combination of the two? Now, combined ones, I will cover in a different video. And maybe I'll just wait until then, because I think this particular video is already going to get a little bit long. Okay, so we did just horizontal, just vertical. You'll have to watch the next video to see what the combined looks like. Okay, so let me set up and we'll look at reflection. Okay, here we are now for our second transformation type, and it's called reflection. Now, as we go through this, look for patterns of thinking. Our pattern of working through this is going to be the same for each transformation. So you just need to keep track of what each of these transformations do graphically. The thinking pattern will be the same. You're going to have to look at the representation other than the algebraic and graphic. And again, I hope you're taking notes for this. So we're going back to the algebraic reflection. Here's our original function. And we also have horizontal and vertical. This time with reflection, we're dealing with a change of sign on either the x variable or the y variable. So let's follow our algebraic thinking again, taking the new compared to the old, and we'll see how this pans out. So if we look for the x's, our negative x squared has replaced the original x. I mean, not x squared, but our second, in our second function, the x is now negative, replaces x subscript 1. So if we want to compare the new to the old, our new function is a negative of the old. That's going to be interesting. Whereas the y is still the same as the original. There's nothing done outside the function. It's only inside the function on the x. So this is what happens. And if your original x is positive, it means your new x is now going to be negative. If your original x was negative and you multiply it by a negative, that means your new x is now going to be positive. What does that mean? It means that you're going to get a reflection over the y-axis. In other words, your positive x becomes negative x, your negative x becomes positive x. You get a reflection over the y-axis, okay? If you have a vertical reflection, by the way, this is horizontal, okay? But it's over the y-axis. If you compare your x2 simply replaces x1, meaning no change to your x values, your y2 is a negative of the original function. So in this case, your x value stayed the same. So if it was positive, it stayed positive. If it was negative, it stayed negative. But the y values changed. So if it was positive, it became negative. If it was negative, it became positive. So what this creates is a reflection over the x-axis, okay? So if you reflect over the y-axis, or if you reflect, here's your y-axis. If you reflect over the y-axis, you're going horizontally. If you reflect over the x-axis, your x-axis runs this way. If you reflect over that, you're moving vertically up and down, okay? So this is the algebraic mental way of thinking through it. This is possibly the way Cambridge maybe could describe it without doing the algebraic part. Now let's look at a graphic illustration. Okay, here is our visual example. This time, instead of using the reciprocal function to illustrate it, now I will use the square root function to illustrate the reflection transformation. So if this is our original, this is what the parent function looks like, the most basic. So if you're at 0, 0, that's the endpoint. If you were at 4 on the x, that would be 2 on the y. If you were at 9 on the x, it would be 3 on the y. So you see it gradually curves and smooths out the farther you get along the x-axis. I'm not going to worry about our 3 points of reference right now, just worried about the basic picture so that you can understand these transformations. Here would be a horizontal example where the negative is on the x. So remember, if the negative is on the x, it's going to reflect over the y-axis. And if the negative is on the function itself, meaning on the y, notice you could divide the negative over and it's on the y, or divide it over here, doesn't matter. This is over the x-axis. Okay, so if you flip over the y-axis, that's horizontal transformation. If you flip over the x-axis, that's vertical movement. So notice we have domain statements. Again, you should, when you see those domain statements, you should be thinking about that. That enriches your understanding. So because this is negative, means our x value has to be less than 0. You might look at this and say you can't take the square root of a negative, which is true. That's why our x values have to be less than 0. So the x values have to be negative so that we end up with a positive in the radical. Over here, it's just x. So our x needs to be greater than 0, okay? So what this means is this is going to flip over the y-axis. This is going to make our graph go this way. Notice our x values are now negative. Our x-axis, we're moving in the negative x values, which gives us positive in the root and a positive value for y. Over here, we have a negative on the outside. This is going to flip over the x-axis, and this is going to end up going like this because our x values are still positive because you have to have a positive in the root. But that root, after you take the root, now becomes negative, which means your y value ends up going down, okay? So here's a reflection over the y-axis. Here's a reflection over the x-axis. This is horizontal, vertical. We looked at them separate. In the next video, we'll see what happens when you combine them, okay? So let me set it up for our third one. Okay, here's our third and last one. Hang in there. I know that this is quite long, but it's really important for you to understand what's going on here. And now we're on the stretches. Technically, it's just called stretch. Shrink is just my part that I add to it. These are the ones that visually are challenging to know which it is. It's quite easy to see if a graph has been moved left or right, up or down. It's also quite easy to see if a graph's been reflected left or right or up or down, usually, not always. But when it comes to stretches, those are the most challenging visually. So it's very important that you understand them algebraically, conceptually. So really work on your mental understanding here. It will help you know what to look for in the visual, okay? So here is our original function again, our first or original. The horizontal, again, is going to be attached to the x, whereas the vertical is attached to the function itself, or the y. So how do we think through this? Again, the pattern is just the same as we did previously. We want to compare the new to the old. So our new x value has this a attached to it that replaced the old one. Meaning, if we take the new compared to the old, it's going to be 1 over a, or it's going to be a fraction of the old. This is usually going to line up with your shrinking because you're taking a fraction of it. It's going to get smaller. And your y value, of course, is staying the same because the change took place inside the function, not outside the function. Now, how would Cambridge maybe represent this? Well, what this is going to cause is your stretch is going to be parallel, so I'm using parallel indicator here, parallel to the x-axis. So in other words, your x-axis values are being stretched in a horizontal direction. So it's either going to go like this, or it could be a shrink where it's still, I like to say shrink or shrunk on horizontally on the x-axis. Okay, that's what you're looking for. Over here, your x2 simply replaced the x1, no change for the x. The y2 now has become a times y1. This is going to be more of your stretch because it's getting multiplied bigger. And the way Cambridge might describe this would be a stretch that is parallel to your y-axis, okay? So you're being stretched this way. Can be made bigger or smaller, but generally bigger along the y-axis, okay? So this, again, is the algebraic way to think through it. It's also a way that could be used to describe it. Now, let me show you a visual representation of this. Okay, you ready for the graphic illustration? Now, in the first one, we're now down, I forgot to move my little marker here. Now we're down on stretch. For translations, I used the reciprocal function to illustrate it. For reflection, I used the square root function to illustrate it. Now for stretch, I'm going to use the quadratic function to illustrate it. Really, the quadratic function is probably the one that you need to pay attention to, I would guess, the most, especially since the first unit was quadratic. So Cambridge loves to integrate functions with quadratics. But you should be able to apply this to any parent function. It should not matter what the parent function is. Once you understand how these work, you just simply apply it to the parent function. So now we're going to apply it to the quadratic function. Now, if you notice in this one, it's horizontal. Our a value, I just chose 2, is multiplying the x. Notice it's in the parentheses, whereas over here, the 2 is outside the parentheses. It's multiplying the function itself, meaning that it's more connected to your y value. You could see you can divide the 2 over here and have it connected to the y, although it would be 1/2 y, okay? But as far as the new function compared to the old function, it's still 2 times the old function, okay? So to help us graph it, of course, we want to simplify it a little bit. So I would change this to y equals 4x squared. So notice that a horizontal stretch can actually be converted into a vertical stretch. So a horizontal stretch of, and remember, actually, maybe I should do this first, because stretches are confusing. So let's look at the algebra part first. Our 2x, this is our new function, replaced the old x. What we're looking for is actually a shrink or a stretch of 1/2 the original along the horizontal. Okay, that's what we're looking for. But as you can see, this also could be written as 4x squared, meaning it should also have a vertical stretch. We're going to focus on the horizontal stretch. We'll come back and compare this because this is actually a vertical stretch. This is what we're going to look for, but I need this form for graphing, okay? Now over here, our y, our new y, is actually twice the old y, okay? So let's graph this one. Just remember, I'm going to move this up here so that we can refer back to it. But I wanted to do the algebra thinking first. This is going to be a horizontal stretch parallel to the x-axis, okay? So when we go to graph this, graphing it, our vertex is actually still at the origin. So if we have And if we take a -1, here's our 3 points of reference. Now, it's a little difficult to see the difference here, okay? So let me put the original function on here. The others are quite easy to see without putting one on top of the other. With stretches, it's more challenging to see visually. That's why it's important to understand what you're doing algebraically. So if we were to put this on top of this, this would be 1, 1, and go up like this. And it would also be at 2, 4. This one would be here and up here. Okay, so what we're looking for horizontally is, remember we said that our new value is half the old one, horizontally speaking. So from 1, this moved back to 1/2, and this moved from 2 to 1. So 1 to 1/2, 2 to 1, we're taking half of the x values. That is what is happening. Notice -1 shrinks to -1/2, -2 shrinks to -1. So it's a horizontal stretch, although I call it shrink because it's getting smaller, not bigger. And it's referring to the horizontal movement, okay? We're going to come back to this, but let's look at this first. Here, if we do this one, we get, again, the vertex is here. If we take 1 squared 1, we get 2. And if we take 2 squared, well, that's going to go up to 8. I don't think I have room for 8. So this is going to go up really fast. If I go to -1, it's going to go up here. And this is going to go up this way really fast. It's going to go off the chart already. Now, if we again, it's almost looks similar. So the only way to really compare it is to put it on top of each other. If we put the original function on it, it would be 1, 1, 2, 4, and this way. Now remember I said that this comes up and actually goes up to 8. The dot that's actually up from here is at 8. Whereas the dot that's down here is at 4. Okay? What you're looking at here is a vertical stretch. So it's being doubled. So this, when our A was 2, our stretch is by a factor of 1/2. Here, when our A was 2, we have a factor of 2. This is our stretch factor of 2. This is our stretch factor of 1/2. 1/2 horizontally. This is a times 2 vertically. Notice we started with a 1 and we now get 2. Started with a 1 and we now get 2. If we go at the 4, it comes all the way up to the 8. The 4 right here times 2 now becomes the 8. Obviously, the graph again looks narrower, but you actually stretch these values higher. So the 1 went up to 2, the 4 went up to 8. You've doubled each y value. The y values have been doubled, so you're stretching it vertically This one, we're actually shrinking it horizontally. So this one, you're wanting to look at the vertical movement, and this one, you're looking at the horizontal movement. Now let's go back to here to show how one can actually be the same as the other. If we compare this where we changed it, we multiplied it out, and we actually made it into a vertical stretch, it's now a stretch factor of 4. Well, if you go vertically, notice it goes from 1 to 4. 1, 2, 3, 4. From 1 to 4. So there is a stretch factor of 4 vertically, but there's a stretch factor of 1/2 horizontally. So again, these can be very confusing, especially when you look at all these parabolas and they essentially look basically the same. You don't see the obvious transformation like you do with the translation and the reflecting. They all look the same, and unless you put them on top of each other and actually look horizontally or vertically, it's almost impossible to visually tell what's going on. What's important for you is that you can be able to figure it out algebraically. If they give you some sort of a stretch factor, parallel to the x-axis, stretch factor parallel to the y-axis, or using horizontal or vertical, you should be able to plot or graph, sketch the appropriate parent function that does that particular scale factor in the direction that they indicate. So this one is going to be the challenge for you. Again, I'm sorry I don't have actual Cambridge past paper questions for you, because this is in the new syllabus and haven't seen any past papers yet. But you've hopefully mentally have a pattern down of how to process it. And also you can see the ways of describing it, and you can see the graphic representations with the parent functions you're familiar with. So this is going to end our part 5. I will make a part 6 video where we looked at combining transformations, and that's going to have a little different twist in some cases. It will also give us a chance to review in case you still don't feel confident yet. So it's been long. Sorry for the length of the video, but I hope that mentally you're starting to hopefully understand what's going on, and we'll see when the exam papers come out. Hopefully you can apply what you've learned to those exam questions. Thank you for listening. Thank you again for joining me in the Zoom room.